Hello, Royals. For lesson 4.5, we are going to look at transformations of primary trig functions. So let's review. From 4.4, we have been introduced to reviewing our sinusoidal functions and our new trig function, the tangent function. If we have f of theta equaling the sine of theta, then we are looking at a sinusoidal function with an axis of the curve of y equals 0, an amplitude of 1, so a maximum of 1 and a minimum of -1, a period of 2 pi. Our original period is 2 pi, one full rotation of a unit circle. And our y-intercept is an axis point on the rise. So we go, let's see here, let's just set up our frame. Axis maximum, axis minimum, axis, like that. If we want to sketch one full cycle, let's make sure that we're always changing curvature. Should never be linear. Concave down when you're above the axis of the curve, concave up when you're below the axis of the curve, and get it a little bit of a tail to remind your reader that it continues forever. Okay, we should always be labeling at least, let's call it like 5 key points, I suppose. Today, when we start transforming, if these values aren't changing, I might forget to label them. I should always be labeling them, though. Let's see if we can squeeze the cosine curve right on here, so I don't need to draw another frame. Tangent curve, though, we'll give it its own frame. Cosine curve has all of the exact same properties as the sine curve, except its y-intercept is 1. So we go maximum, axis, minimum, axis, maximum. It looks like a sine curve because it is a sine curve. It is the sine of the complement of theta, the complementary sine. Not cos, but cosine. There's G. The tangent curve, I don't know, let's use h of theta equals the tangent of theta. It's a little bit different, isn't it? I mean, we have an axis of the curve, which is an axis of inflection, just like with the sine curve and the cosine curve. But we don't have an amplitude, so I can't really frame my curve. Let's sketch from 0 to 2 pi. Here's a half rotation at pi. From our unit circle, we discovered that the tangent of pi by 2 doesn't exist. We have a vertical asymptote right there, and the tangent of 3 pi by 2 doesn't exist. Got another vertical asymptote right there. And we are concave up now when we're above the axis, and concave down when we're below the axis. Not horizontal. You can call it a linear route. It's actually more of like a trigonometric route, but our rate of change is not 0 when we're on the axis, we'll discover. And when we sketch this curve, one of the things that we discovered is that the original period of the tangent curve is pi. So like we said, if in the past we were using a formula for transformations that said your new period is 360 degrees divided by your absolute value of k, that's going to be wrong for 2 reasons in this course. 1, we're using radian mode and not degree, and 2, we might be looking at a cotangent curve or a tangent curve that do not have an original period of one full rotation, but a half rotation. Okay, transformations of these curves done in the same way as other functions. I am just going to start combining transformations. You should be able to handle the basic transformations on your own from the lesson. Let's, I guess we'll sketch, but we're going to identify the key features before we do this. Let's start with f of theta equals 3 times the cosine of theta minus 5. So just be careful here. Make sure that you understand that first we undergo a vertical stretch by 3, and then we have a shift down 5, or a vertical translation down 5. Where we need to be careful is because the vertical stretch doesn't affect our axis points, we often start by identifying our axis of the curve being y equals -5. Of course, the stretch has happened first, but the shift is maybe easier to track. Okay, reading where my maximum is on this curve is a little bit more challenging than reading where my axis is. So I start with my axis, the curve of y equals -5, and notice I didn't start with my x-axis or my theta axis because maybe I won't even touch it in this example. From there, I use the fact that my amplitude is 3. That means that my maximum is going to be 3 higher than -5. That's going to be at -2. And I'll try to create a square here, framing where my maximum is going to be and my minimum is going to be. Minimum is going to be 3 lower than -5. That's at -8. And I draw a non-reflected cosine curve, meaning that I go from, or I decide where to start. I guess I'll start at the point that would have been mapped from 0, 0. Usually we're asked to sketch one cycle of. That might be different for a tangent curve, though. Halfway between a maximum and a a maximum and a maximum. We can get a little bit more accurate if we want to use a ruler. You might be artistic enough to, I'm not sure it's artistic enough to be able to spot what's halfway between 2 points. Working in pencil would be a better idea. As usual, projecting or recording in pencil doesn't look as nice as with pen. So yeah, if I mess up, I might just have to scribble out the whole thing. If you mess up, hopefully you'll be able to just erase it. Let's label the curve. And yeah, notice that none of our independent values have changed. You could imagine that this is the image of the point 0, 0. So it hasn't been shifted left or right. That's still 0. This still occurs at 2 pi. My quarter period is still pi by 2. So I'm counting up by pi by 2. 0, pi by 2, 2 pi by 2, 3 pi by 2, and 4 pi by 2, like that. The mapping statement is not an efficient strategy here. You have 1, 2, 3, 4, 5 points to map, and that would take way too long. We also know that the maximum is always going to be at height of -2. Can you imagine if I asked you to sketch 3 cycles? This wouldn't be much harder. I would just keep going, maybe one to the left and one to the right. Doing a mapping statement for 3 cycles would be like 15 more points, or 15 points total or something like that. Okay, notice what's not on here. I didn't bother drawing my y-axis or my f of theta axis, and I definitely didn't bother drawing my independent axis. Be all the way up here. Maybe I don't care about that. Maybe I want to center my view or my screen on the interesting part of the curve, which is not up here. And that means that I can label my independent values down here. Some people like labeling them on the axis of the curve. I feel like it kind of gets in the way of my curve sometimes. I guess you could label it up above the maximum. I like labeling it down below the minimum because I know I don't need this space at all because my curve is bound between -2 and -8. I can see the range from a sketch as well. Okay. If we were asked to do a reflection, again, let's just recycle this frame and say we were asked to sketch. Come on. G of theta equals -3 times the cosine of theta minus 5. Again, I'm going to urge caution here. This is not just going to be a vertical reflection of this curve. Okay. It would be a vertical reflection of that curve and then shifted down 5. If I reflected this curve vertically, it would go waka-chow all the way up there. What you can do, though, is imagine that here we were starting with an original cosine curve. We stretch it vertically by 3, and then we shift it down 5, and that's where it ends up. Here we would have reflected and then stretched, or stretched and then reflected and then shifted down 5. So it's going to look like a reflection across the axis. That's okay if you're thinking that way, I suppose. Okay. Often students will say, oh, it's a vertically reflected cosine curve, so I am going to begin sketching at a minimum. You should be careful about saying it starts at a minimum because, of course, this curve does not have a beginning or an end. It has an unrestricted domain. Let's get that good curvature going. There we go. Okay, all of the same sinusoidal properties as the curve above. Same amplitude, same axis of the curve, same period. It would have a different y-intercept. It's just shifted, phase shifted. Our printed lesson doesn't have a ton of tangent examples, but there's not really a lot to do with them either. Like without having an amplitude, you can pretty much ignore vertical stretches. I'll illustrate that here. Say, ask you to sketch y equals the opposite of the tangent of x plus 4. Let's try walking through the transformations. I would begin with the tangent curve. And this one I'm going to sketch 2 cycles of. I'll sketch from, maybe instead of 1 cycle of, it should have been from 0 to 2 pi or something like that. This will change when we have shifts and changes in our period. But right, so original tangent curve, vertically reflected, would now look like this. That should be invariant right there. Okay, and then I shift it up 4. Well, I'm just going to track my axis up 4. So wherever I center my sketch, I'm going to call that height 4. So guess what? This is y equals 4. It's the axis of inflection of my curve. And then I sketch myself a vertically reflected tangent curve. Let's draw from an axis to an axis to an axis. Halfway in between, we'll have a vertical asymptote. Halfway in between there, we'll have a vertical asymptote. And instead of curving upwards, we curve downwards, not horizontal. And those might be getting a little bit too close to horizontal. Coming in like that. Sign change. Unlike with polynomial functions or ratios of polynomial functions, we can't rely on the exponent anymore to determine sign change. We need to understand that tangent ratios change sign as we go around. As we go around in standard position. What else do we have to label here? I suppose I should label that as, no, I don't have a minimum where I can label, so I kind of need to squeeze these labels in here. That's 0, that's at pi, that's at 2 pi. Let's label the curve. Oh, and our asymptotes. Let's label this. So technically this is the theta axis. You could label this vertical asymptote theta equals pi by 2. Maybe we should. But it seems quite popular to just keep labeling vertical lines x equals, even if there isn't an x in the application. I guess I'm okay with both. So yeah, notice how there's no vertical heights like a lot of our rational functions. So if I asked you to sketch y equals, I don't know, 9 times the tangent of theta plus 4, there you go. It's the same curve if I want it to be. It would be 9 times steeper. The rate of change would be 9 times greater, multiplied by a factor of 9, 9 times greater and 9 times smaller technically, because all rates of change are negative here, than the rates of change of the original curve that I drew, but I'm just going to pretend that I stretch my scale. Okay. Let's talk about some horizontals. There are a couple of homework questions for this day that mix up horizontal and vertical. We are going to be tackling some strategies for that in the next lesson. But you should be able to combine the two for a bit of practice with tonight's lesson. Let's try f of theta equals the sine of 2 theta minus pi by 6. So if we wanted to list our transformations, notice I stopped listing my transformations on the last page because with trig functions, we can usually just identify properties. I should be able to list transformations still. I have a parent y equals the sine of theta that has undergone a horizontal stretch by 1/2. It's in a factored form, so I can read off my transformation, and then a translation right pi by 6. Okay. Now, I usually will be thinking about this transformation, but I don't often think of the horizontal transformation. I tend to say that my new period is going to be a horizontal stretch of whatever my old period is. And in the general case, my horizontal stretch is going to be the reciprocal of the absolute value of k. So I can just build this little formula myself. I don't need to remember it, which means I'll never forget it. What I remember is that I can figure it out on my own. And so in this question, I would probably just say, well, my new period. Give me a sec, Riles. There we go. My new period is going to be my original period, which was 2 pi, because that's the original period of a sine curve, divided by the absolute value of 2. So I have a new period of pi. Now, my full period sure is an interesting value, but when I sketch my curve, there's a full period right there. I'm usually more interested in what a quarter period is. So I always calculate what my quarter period is. In this case, my quarter period is going to be pi by 4. Reading from left to right, I usually record this information first, but I actually don't want to start with the pi by 4 because pi by 4, my period, does not show up on a curve, especially when it's been shifted. I'm not going to see, I don't think I'm going to see any inputs labeled pi by 4. Okay. What I'm going to do is I'm going to sketch myself a sine curve. And notice I have not stretched, I have not shifted, but I can deal with those in a sec. In fact, maybe I'll just switch this example in a sec. I can just find where my frame is going to exist. So that's no problem. It's looking okay. So yeah, this curve acts as the curve of y equals 0, amplitude of 1, so maximum of 1, minimum of -1. And I'm going to draw a non-reflected sine curve that's been shifted right a bit. You know what? I want to start sketching right here. So I'm going to start sketching there, and I want to end sketching here. This would be much harder on a grid because I'd have to worry about the values of all of my squares. But we have the freedom, once again, because we're working with sketches, not graphs, that I can draw whatever sine curve I want. And I want to draw this sine curve right here. In fact, you should be able to, if I give you a sine curve or any portion of a sinusoidal curve, you should be able to label it so that it would match this equation. Speaking of labeling, let's get that down. So the first piece of information that I'm going to use, I suppose I know that from here to here is going to be pi. But again, that's not a position, that's a difference or a change. I was going to say distance or time, it's neither. It's a change in my independent variable. If you think about a mapping statement, this curve, original curve, would have been horizontally stretched by 1/2 down to, I don't know, something like that, I guess, or something like that. Great, that looks awesome. And then shifted right pi by 6. Well, that point on the axis right there would have been shifted right pi by 6. So I'm just going to follow it. And now I'm going to start sketching my curve, or I'm going to start labeling my curve because I've already sketched it at pi by 6. Now I know this point right here is going to occur at pi by 6 plus pi, or 7 pi by 6. I could label that. In fact, I may, lightly. But then students that do this often feel the need to, okay, figure out what's halfway in between there, and then what's halfway in between there, and what's halfway in between there. And that's not efficient. Just add quarter periods. Okay. Now, this is going to require a little bit of fraction work, but it's very close to, let's say, grade 7 level fractions. We need to do pi by 6 plus 1/4 period, which is going to be pi by 6 plus pi by 4. That's going to be 2 pi by 12 plus 3 pi by 12. That's going to happen at 5 pi by 12. Points labeled, or positions labeled. Now I add another pi by 4, or another 3 pi by 12. In fact, maybe since I'm seeing a common denominator between 6 and 4 here, I could just ghost this in as I'm adding 3 pi by 12s. These numbers should always be reduced, though. So when I add 3 pi by 12 to 5 pi by 12, I'll get 8 pi by 12, but I want to reduce that down to, what, 4 pi by 6, 2 pi by 3. Okay. Fraction work. What we're doing here is 1/6 plus 1/4, 5/12 plus 1/4. Now I'm going to do 2/3 plus 1/4. I might benefit from keeping my ghosted in answer here of 8 pi by 12 plus 3 pi by 12. That'll give me 11 pi by 12. And then 3 more pi by 12 will give me 14 pi by 12. And guess what? 14 pi by 12 reduces to 7 pi by 6. We talked about advantages and disadvantages of radian mode, and it often has been identified that students dislike radian mode because it means they have to know fractions. I don't accept that argument to say, you mean I have to be able to add 1/6 and 1/4? Yeah. Yeah, you need to know how to add fractions. Okay. Here, let's change the question a little bit. What if this was, I don't know, 3 sine of 2 times theta minus pi by 6 plus 1? Well, all I would do is change my axis of the curve to y equals 1, change my amplitude to 3, change my maximum to 4, change my minimum to -2, and we're set. Or what if we did -3 times the sine of yada, 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 yada? Well, it would be same axis of the curve, same amplitude, same maximum, same minimum, same shift right pi by 3, but we would be shifting, pi by 6, shifting our axis point on the rise over and changing it into an axis point on the decline. So again, it's going to look like it's been reflected across the axis of the curve. Like that. There, we'll call that one g of theta in the red, and there's g. Okay. Let's try a tangent curve, and then we'll call it. H of theta equals the tangent of pi by 2 theta minus sorry, I'm looking at my example and I think I need to change it. Let's do pi by 4. So when your horizontal stretch is an integer, like not a multiple of pi or a rational number, then your period tends to be multiples of pi and your key angles tend to be multiples of pi. This usually happens when your period's related to an angle. When we want periods that aren't angles, like for times or stuff like that, we generally need stretches that are multiples of pi. Now, thinking of this as a horizontal stretch by 2 over pi can be a little bit confusing because I'm stretching by an irrational number. I mean, I should be able to handle it. An original change of, say, pi when stretched by 2 by pi is going to be a new change of 2. But I don't even need to think of horizontal stretches if I build my formula first. Okay, and again, I build my formula. I don't remember my formula. Perhaps before we get into the period, though, we should make sure that this is in factored form. Oh, no, it's not in factored form. Let's get it in factored form. Let's remove a factor of pi by 2. You can ask yourself a check-through distribution. Pi by 2 times what gives you pi by 4? That looks like 1/2. Or you could even do a division off here on the side. You're doing pi by 4 divided by pi by 2. You could, if you don't see the pi's dividing out, write it as pi quarters multiplied by the reciprocal of pi by 2, which is 2 by pi. And then you receive, there's your horizontal stretch factor there, 1/2. Okay. Now I'll get my new period. Actually, here, I'll show you, we can draw our sketch first, or the portion of our sketch. No frame here. We were asked, what were we asked to sketch? Oh, we changed the directions. Right. I don't know. Let's sketch 2 cycles. So we'll have 3 axis points and 2 vertical asymptotes. And we're going to be increasing up like that. Again, I'm going to encourage you to try this method of like sketching first. You say, but you don't know what your axis is. Wherever it is, I'm going to label it right there. Well, you don't know how far it's been shifted. Okay, so I'll label that there. Like I don't start by drawing my origin. Why would I care about the origin for this question? Yeah, and then I realized that in this question, I'm not going to get the period first. I realized I kind of want to know where this point that used to be on the origin is going to be shifted. It's shifted right 1/2. So let's label that as a height of 1/2. Sorry, not a height, independent value of 1/2, input of 1/2. And now we can get our period if you want. Our new period is going to be our original period divided by the absolute value of k. For the tangent curve, our original period was pi. We divide by the absolute value of k, pi by 2. And you can multiply by the reciprocal if you like. Try maybe just dividing out the pi's and then multiplying by 1 in the format of 2/2. Those will divide out and you'll get a new period of 2. I mean, you can go pi divided by pi by 2 equals pi over 1 multiplied by 2 over pi, and then divide them out. But we should be used to dividing by fractions now, and hopefully we have some efficient strategies. Okay. Quarter period for the tangent curve isn't as useful. With sine curves and cosine curves, we have a full period, another axis point at a half period, and then turning points at quarter periods away. So quarter periods between axis, turning, axis, or inflection, turning, inflection. Where here, this is our full period right here. And here's our half period. So maybe we don't need the quarter period. Maybe I'll just calculate my half period. My half period is going to be half of 2 is 1. So this asymptote is going to happen at theta equals 1 and 1/2. And this right here is going to happen 1 later, so that's going to be 2 and 1/2. This will be 3 and, whoops, theta equals 3 and 1/2, and this will be 4 and 1/2 right there. I mean, you could just count by 2 halves as well and go 3 halves, 5 halves, 7 halves, and 9 halves. And that worked great. Okay. Just like all of our other curves, maybe more so than our other curves, sketching trig curves should be done in an efficient manner. No grid, no calculator, no table of values, no mapping statement. Give it a shot.